Hey everybody, welcome back to Private Pilot Ground School and welcome to our performance and our weight and balance section. This is chapter 9 of our Jeppesen Guide to Flight Discovery. Chapter 9, chapter 8 of the Guide to Flight Discovery. Chapter 8A is the one we're talking about today. The objectives of this video and this lesson are to learn how to use data supplied by the manufacturer to predict airplane performance. So if you build your own airplane, this might not help you out very much because you got to make your own charts if you do that, right? So, but fortunately for you, Cessna, when they made the aircraft, they figured out how well it would perform and they put it in the POH for you, and we're going to learn how to use the data supplied by them. So, a quick peek ahead, these are the charts that we're going to be using in this video and in this class. And then, of course, we're going to talk about takeoff, landing distance, fuel consumption requirements, and overall, you're going to pass a quiz and learn how to use these charts to predict performance. So, once again, Chapter 8A is the one we're talking about, and we're going to use the POH. And you're going to see some figures from the knowledge test supplement as well, because you're taking an FAA test when you're done with this. So we're going to use some of those figures and make sure you know how to use them. Some of the charts are the same, the tabular format. Some of them are a little bit different, and I'll talk you through how to use those. So airplane performance, of course, if you haven't read chapter 8A, by the way, then go ahead, pause the video, go read it, and come back, because this will make a lot more sense if you do. So different airplanes are designed differently because they have different missions. You can make them to go fast, you can make them to go slow, but generally you can't make them do both things. We can affect that by having flaps and Fowler flaps and raising and lowering landing gear to help things go faster and make them land better. But generally, you're going to see those dirt strip off airport, you know, boondocking airplanes are going to be tail draggers to get the prop away from the ground. They got big O wheels, but they're not going to be able to go very high, very far, or very fast because they're designed to go really slow and land on rough terrain. Okay, but you're gonna have a hard time fitting a Airbus A380 or a Boeing 777 into a gravel strip in Alaska, but they can sure go higher and faster, right? So you design them for cargo. Again, of course, those large commercial aircraft are designed to where you can either put a bunch of cargo in them or you can put cargo and people. Most of the ones that you see and all the ones you fly in are passengers on the upper deck and cargo down below where your bags go. The point is, there's different airplanes for different jobs, so you would pick the one that you need for your mission. So here's an example of 3 different performance charts. Okay, so these two are from the Airman Knowledge Test Prep or the Airman Knowledge Test Supplement. Here is a very simple tabular format like we see down here from the Cessna chart. And on this one, they would say, look at this figure, and this figure is only one aircraft under one set of gross weight and circumstances, and they ask you questions. They might say something like, at 5,000 feet and 41 degrees, what's your ground roll going to be, or what's your takeoff going to be? Or they start giving you headwinds, and now you have to deduct 10%. Or they say, the temperature is hotter than standard, you have to start adding 10%. And then for grass runways, you have to add 20%. So the notes are pretty important. I'm going to cover that again and again on here. And here is the graphical one. These are really handy on a computer because you can draw on it and then erase it. On the paper one, it's not so handy because you can't draw on it and then erase it because there's this big white line where there used to be stuff. But these are pretty handy because in the field you don't need a calculator. You literally just draw from one to the other. And then we're going to spend most of our time talking about the Cessna charts like you see here. My point here is different manufacturers make them differently. Piper loves to make them like this, Cessna loves to make them like this, and then the FAA tries to make it easy on you and they give you just one at a time like that. So let's go over the table format charts. Here's just a much bigger version, and here's what they show on here, okay? If you don't know, just read it, all right? You see in the Cessna chart right here, this is a bad example because I don't show you the weights. There's multiple Cessna charts with different weights. I'm going to show you all the Cessna charts later on. We'll go through the video first, and then I'll do demonstrations as we go on. Now you'll see how they're labeled. So basically at this weight, and if you were at a different weight, you would look at a different chart for this airplane. at these different density altitudes. So sea level at 59 degrees Fahrenheit is standard ISA, International Standard Atmosphere conditions. And this is going to be the best performance you get, the least amount of distance you need to get airborne and the least amount of distance you need to climb to get airborne and then continue climbing to a 50-foot obstacle. So this is meaning that from the start of your takeoff roll to the time your wheels leave the ground, it's supposed to take around 445 feet. From the beginning of your takeoff roll to the time that your wheels are 50 feet in the air, it's going to take 1,075 feet. Now, this is if you do everything perfect, if the airplane's perfect, and if the weather's perfect, and if the tarmac's and the runway's perfect, then you can make those numbers. But very rarely will you ever make those numbers. You're going to need a lot more distance than what the checklist usually, than the POH usually says you need. So my point here is at different altitudes and temperatures, they're saying that at this density altitude, here are your numbers. And then I need to, and then at this density altitude, here are the numbers you get because it's higher elevation and it's supposed to be colder temperature. At this density altitude, here's the performance you can guess. So they could have made this chart differently. They could have just said listed gross weights on the side and listed density altitudes and made you do the math to figure out what the density altitude is under those conditions. Or they try to make it easy on you. So again, if you're in the airplane or you're in the field and you don't have a calculator, and then you can use these to at least approximate your answer. So again, the difference here would be ground roll. I already explained that. Your book does a pretty good job too. And the 50-foot. And then the notes are so very important. Specifically for this chart, if there is a 4-knot headwind, and if otherwise this would have been your answer for ground roll, you would deduct 10% of that, or 470 minus 47, or 470 times 0.9, or there's ways to do it, all right? And we'll go over some of those examples. Speaking of, let's bring up a calculator. That's going to come in handy later on. Now, the graph format charts don't require a calculator, or generally they do not, but they do require some graphing, hence the graph. So this looks overwhelming because there's so many lines and so many arrows and so many sections. Let's just break it down into smaller sections for you and make it easier to understand, all right? The red arrows here are their examples. So on every one of these charts, they give you an example, and that's what the red arrows are. This is straight out of the FAA test prep book here, okay? So you don't use these red arrows for your calculation. This is how they got their answer using this information. So with all these charts, really, you just plug in the information you have, and it gives you the information that you don't have, the information that you're looking for, the information that you need. And of course, you only get these distances if you do everything correctly and as it was designed by the manufacturer. So if you come in too fast, if you're a little heavier, if you don't do it just right, if you don't get on the brakes as well, which means if you don't have good brakes, or if you don't have good wheels, or if it's a slick surface, you're not going to get anywhere near any of these numbers. You're going to need a lot more runway to take off or land. So again, give yourself a good safety margin. So the lay of the land here basically is, again, that's the red arrows are just the example there. And so they're saying with these conditions, this is the answer they got. And they talk you through how they did it. So you can see at 25 degrees Celsius, they came up and they intersected a line that corresponded with 3,965 feet. Pressure altitude, and then they move on to the next chart. And then they follow the guideline down to where it intersects their weight of 2,814 pounds. And then they're done with that section and they move on to the next one. And then they follow the reference lines down to intersect the 9 knots. And then they're done with that section. They move on to the next one. So each one of these 4 sections you're seeing, take a different input and either move the distance up or down. So the higher the temperature, the more runway you're going to need. The higher the altitude, the more runway you're going to need. The lighter you are, you see the lines go down, the less runway you need. The more headwind you have, the lines go down, the less runway you need. If you have a tailwind, the lines go up pretty steeply, the more runway you need. And then this is, usually it's a one or the other. It's either 0 feet or 50 feet. So there's kind of no in between on most of these. And specifically in their question here, they only asked us, I'm sorry, they did ask us the ground roll and they did ask us the total over a 50-foot obstacle. And their example is missing an important line here. The important line should be a red line following up on the reference line here to get the answer that they were looking for on the 50-foot obstacle. So it was missing this line. All right, I didn't make it, but I just added it in for you. That's what it's supposed to look like. So here's the 4 sections again. When you remember, the definition of density altitude is pressure altitude corrected for non-standard temperature. So by intersecting those two givens that you have, the temperature that you have and the pressure altitude, you would make those two intersect. So if you have this in their example here, we're at almost 4,000 feet pressure altitude. You see where it says 4,000. If you wanted to, you can go ahead and highlight that line and move it all the way across there. And then you would enter here at 25 degrees Celsius, and where those two lines intersect, that has done its job. This chart has moved the number up or down where those two lines intersect. And then you see, you just go off the page. You go to the next one. You click enter or tab, and you don't actually click enter or tab. And you intersected your two given values, and then it goes off the chart to the next section. And the next section on this graphic chart is compensating for weight. So the lighter we are, the less distance we make. So this, what these reference lines are for, is you follow them down. They guide you down. You do your best to parallel these lines until you intersect your new value, which is almost 2,800 feet. It's a little bit greater than 2,800 feet. So where we entered the chart here, it goes down until it intersects our 2,800 value. Okay, so this is one new given along this line, and the other given was weight. Once you've done that, once they've intersected, you're done. Move on to the next chart. So really, these arrows shouldn't be there because we didn't need them, because we stopped following the line down once we intersected our 2,814 line. And then you move on to the next one. The next chart here compensates for wind. If you have a headwind, it decreases your distance. A tailwind, it increases your distance. So your given here is following the reference lines until you intersect your other given, which was 9 knots. So once you've intersected that point right there, you've finished this chart. It's time to move on to the next one. And this one, if you're looking for the ground roll distance, it's a 0-foot climb. You know, really, it's technically what, a 1/16 of an inch climb, because you're not on the ground anymore. But this is how much ground roll it takes. Runway till the wheel leaves the ground. You just ignore the lines because that's your answer. You go straight across to find the answer. About 1,200. There's 1,250. It's about 1,100 feet. So look at the index marks here. If this is 1,000 and this is 1,500, then this line would be 1,250, which means if I count the dots in between here, this one would be just shy of 1,100. This would be 1,050, 1,100. I'm just shy of it. In the real world, if you put 1,100 feet, you would get this answer correct, okay? They got very specific on theirs, though. And then the other part of it is the reference lines here are, if you are looking for the distance over a 50-foot obstacle, then you just follow the line up where it intersects the end. And on this one, halfway between 1,500 and 2,000 is 1,750. That's probably the answer I would give, because it looks pretty close to halfway between those two given values. And it looks like they gave us 1,700. Pretty darn close. Close enough for government work, right? So that's how those charts, that's what they're showing us. Don't be overwhelmed with it. Don't be overwhelmed with all the other data and stuff they're giving us here. What this one does have is different. This is a landing distance chart. Okay, so this is how much distance it takes after you've landed to stop, or how much distance it takes to pass above a 50-foot obstacle and then land and then stop, is what the difference is between those on the landing chart. And then on this one, it's just telling us that at different gross weights, we would come in at different airspeeds to get these numbers. So again, don't be overwhelmed with all the extra stuff. So what affects our performance? Well, a lot of things. First and foremost, air density. The density of the air is affected by these main things. The temperature. The hotter the air is, the more active the molecules are, and the more they spread out, which means they become less dense. When the air becomes less dense, you make less power because the engine's breathing fewer oxygen molecules to mix with fuel molecules to turn into power. And your propeller, which is moving air, is making less thrust because the air is not as dense. Your wings make less lift because there's not as much air flowing over and under them, which means you fly at a higher angle of attack, which means you make more induced drag. So temperature is not the only thing that affects that, though. If you go up in altitude, obviously the air becomes less dense because there's less air on top of it, packing it down. As the barometric pressure goes down, so the altimeter setting is an indication of the pressure, at a lower than standard barometric pressure, there's less pressure, there's less air, and all the aforementioned things are happening. And then humidity actually has a pretty big effect on that too. Think of it a couple different ways. If a water molecule takes up more space than a dry nitrogen or a dry oxygen molecule, so that one water molecule takes up a lot of space. And then the other thing is your engine doesn't burn water. Okay, it's your internal combustion engine is not capable of splitting the hydrogen and the oxygen apart from each other and then burning them. Okay, so water in your engine can't burn. And there you go. So all those things affect your performance. So think about those, and then that's why our performance charts give us options for altitude and temperature, basically to determine density altitude, so we can figure out with the decreased power and thrust what our performance is going to be. And the other thing that affects us, of course, is weight. The heavier you are, the worse you will perform. Or we say it will decrease aircraft performance because you won't perform as well. So if you decrease takeoff performance, you're going to need more runway to take off because you're not going to accelerate as quickly. You won't be able to climb out as steeply. The heavier you are, you won't be able to cruise as quickly or go as high or go as far. So weight has a huge impact, obviously, on performance too. Now let's talk about the baseline temperature, the international standard atmosphere. Okay, we did talk about this in a previous module, but it's worth repeating because it has a lot to do with all our cruise charts today. So the ISA is just a baseline. It's not what the weather actually is most of the time, but a bunch of scientists got together and said the standard temperature all around the world is 59 degrees Fahrenheit. And let's just start with sea level because very few people live below sea level on a full-time basis, and most planes fly above that. So our best performance is going to be at sea level, and as we go higher, we lose air pressure. We're going to decrease our performance, but we also have to take into account temperature too, because that affects the density of the air. And if you want the other conversions, 15 degrees Celsius is the Celsius version of 59 degrees Fahrenheit. And pressure, 29.92 inches of mercury, is the standard atmospheric pressure on our altimeters here in the Western world. And everywhere else, you would use hectopascals or millibars, and that'd be 1013.2 as a standard pressure if you have moved on from the imperial system. And then if you went out there and measured it, it'd actually be 14.7 pounds per square inch. If you have a gauge out there right now, it probably says 0 because the pressure inside and outside of it is 0. But if it was calibrated to 0 and then you brought it out here, let's say if you had, anyway, if you were to measure the pressure of the air that you're breathing down here on a sea level standard day, it'd be about 14.7 psi. And that's all based on 0% relative humidity. There's usually some moisture in the air, sometimes more, sometimes less, and that actually has an impact on the air density as well. Contrary to what you may believe, humid air is less dense than dry air. So in humid air, you don't perform as well, neither does your airplane because it has less oxygen it can burn in each breath that you take or each intake stroke of the engine of the airplane you're flying. And this is also based off of the standard lapse rate of 2 degrees Celsius per 1,000 feet. So if you remember this from our weather chapters, the standard lapse rate, if you go up 1,000 feet, the temperature is supposed to drop 2 degrees Celsius. And this is pretty standard up until about the tropopause. And here's a handy chart, thank you, from the Cirrus Pilot's Operating Handbook to break it down for us this way. So if the standard at sea level, the standard temperature should be 15 degrees Celsius. Have this handy if you can't do the math, okay? At 1,000 feet, the standard temperature is supposed to be 13 degrees Celsius. At 2,000 feet, the standard temperature is supposed to be 11 degrees Celsius, and so forth. So, without looking at the numbers over here on the side, at 10,000 feet, the standard temperature is supposed to be 15 minus 2 degrees for each of those 10,000 feet. So I would actually personally take 10,000 feet times 2 degrees per 1,000 feet. I'm going to cool off 20 degrees as I go from sea level to 10,000 feet. And if I started at 15 degrees, because that's standard, and I lose 20, 2 degrees per 1,000 feet, remember, it should be negative 5 degrees Celsius when I'm at 10,000, and sure enough, that is the standard temperature at 10,000. Now, it doesn't mean that's what the temperature will be at 10,000 feet. So it's very important that you understand how to figure out what the standard temperature should be, so then you can adjust on the chart for what the ambient pressure and temperature actually is. And if you really want to nerd out for just a second, okay, so 59 degrees Fahrenheit is the exact same as 15 degrees Celsius. And if you really want to know, that's 288 Kelvin. Okay? Uh, if you forget how to convert between Celsius and Fahrenheit, look on your trusty pilot computer, the E6B, or have a chart handy. There's a chart in your POH that helps you with that. So what is pressure altitude? Once again, it's the height above the standard pressure level of 29.92. The best way to determine your pressure altitude is just to set your altimeter to 2992 and read it. But if it is not actually 29.92 degrees, which it very rarely is, that's one way, is to just move your altimeter to read it and then move it back to your current altimeter setting. Just don't forget to move it back. Other ways are there's charts for that, or you can do a kind of a pretty close conversion factor. Basically, for every 10 feet of altitude, you lose about 0.01 inch of mercury. So if I were to change this to 29.93, my altimeter would change by 10 feet. And if I was currently at 30.00, I'm 80 feet higher or lower than what the gauge says. So the easiest thing is just to put it to 29.92. And also, fun fact, as you lose atmospheric pressure as you climb, you lose about 1 inch of mercury per 1,000 feet up until around 18,000 feet. So at about 18,000 feet, the air is 1/2 as dense as it is down here at sea level. So that's why you or your aircraft do not perform as well at those high altitudes. Now, once again, density altitude is pressure altitude corrected for non-standard temperature. I like to consider it as the measurement of the density of the air. It's in the name, right? Density altitude, or how dense the air is. And now, density altitude, it can be affected by pressure, as in by going up in altitude where there's less pressure, or a low pressure system, which means there's less pressure, or increasing temperature, which makes the air more active and spread out, which makes it less dense, or increasing the humidity, which once again, water vapor weighs less than dry air. So wet air weighs less because it's less dense than dry air. So don't just think because it's wet it must be heavy. It's wet, and it's actually, there's fewer molecules in that moist humid air than there would be in dry air. Most of these charts we talk about do not compensate for humidity, so your book says to add 10% to be safe. I personally add 50%. So what I mean there is, let's say if the chart says I need 1,000 feet to take off, I'm not going to try it unless I have at least 1,500 feet. So I like to add a good safety margin. Now, if you're at a high density altitude, like Big Bear during the summer, or even places like Ramona during the summer, Big Bear, even during the winter, is high density altitude, but even low altitude places like Ramona, Montgomery, they end up being a high density altitude, even down here at a close to sea level airport, if it gets hot enough, or humid enough, or the low enough barometric pressure enough. So if you're in a high density altitude, I mean anything above 3,000 feet density altitude, which again can happen down here at sea level on a hot and humid day, then you need to lean the mixture. You should definitely lean the mixture no matter what if you're not using full power. Okay, if you're taxiing, if you're cruising, it doesn't matter what altitude you're at. If you're at that lower power setting, you should always be leaned. It's better for the environment and the engine and your fuel bill too. If you just leave it full rich out of habit, you get less engine performance because the mixture is too rich, because the air is not as dense, and if you're throwing in just as much fuel as you were when there was more oxygen molecules, then it's too rich. It's not stoichiometric, which means you won't have a complete combustion of all the air and the fuel inside your engine. If it gets high, hot, heavy, and or humid enough, it's just completely unsafe to fly. So Big Bear Airport is a 6,752 feet elevation. During the summer, you very rarely see people come and go during the day because the density altitude is so high it becomes unsafe. So they come in the morning or leave at night when it's nice and cool. Okay, we can figure out density altitude by using a chart like this one. Basically, once again, it's just putting your two givens in and intersect them, and it gives you the answer. For this one, I'm just going to make some numbers up. If it's a 90-degree Fahrenheit day, and I'm at Big Bear, which is almost 7,000 feet. So let's just cheat a little bit and use our 7,000 feet line right here. So wherever this line intersects my other line, these are my two given values, they intersect there. Just try to follow it best you can off the edge of the chart. I'm almost 11,000 feet density altitude. So even though I'm only at 7,000 feet above sea level, I'm going to perform, and my airplane are going to perform like you're up at 11,000 feet. That's because it is hotter than standard. If it was standard temperature, I'd be at 7,000 feet and I would feel like I'm at 7,000 feet. But because it's higher than standard, it's hotter than it's supposed to be at that altitude, the air is so much less dense that I'm going to feel, and my airplane is going to fly like I'm at 11,000 feet, even though I'm only at 7,000 feet. And there's many of other ways to do density altitude calculations too. Of course, read up on your chapter and they tell you more about it. And here's an example of an FA test question you'll see referring to this figure, figure 8, in this edition of Chart Supplement. If I go from 30 degrees to 50 degrees, and my density altitude stays, or my pressure altitude stays at 3,000, what happens to me? So on this question here, we're stay at 3,000 feet. They just want to know if I go from 30 degrees Fahrenheit to 50 degrees Fahrenheit, what's going to happen to my density altitude? I'm not giving you the answer options yet because I want to walk through them. So if I wanted to, and don't draw this on the paper book because you'll get in trouble if you do, unless it's yours, then you do what you want. Those lines intersect here, as opposed to if it were 50 degrees Fahrenheit, those lines would intersect here. So all things else being equal, just increase the temperature from 30 to 50, raised my density altitude from around there to around there. Raise it from, 1,400 to about 3,000. So it increased by about 1,600 or so feet. Now let's see what our closest option is. I need to draw straighter lines is really what it comes down to. Because right now my closest answer was the 1300, but let me actually try to do a better job this time. There's our 3000. Looks like it's right at 1500. And there's our 50 at 3000. Looks like it's more like 27. So it looks like I'm going up around 1300 feet from 1400 to 2700. And so I would choose A, and that's going to be our right answer. So that's, don't make it harder than it needs to be. Okay, so this question, you went from there to there, and resultingly my DA went from there to there. All right, so that's a little bit about density, altitude, and those charts. Now let's actually go over a takeoff and landing charts. So first of all, what affects performance? Well, the heavier you are, the worse your performance will be for takeoff. So you're gonna accelerate more slowly. You're going to need more runway to get airborne, and then you're not going to be able to climb as well. Other things that affect that are your configuration. We mean like flaps extended they causes drag, so you wouldn't be able to accelerate as fast or climb out as steep or maybe climb out at all. The runway gradient, that is the slope of the runway. If you take off uphill, you have worse performance because you were going against gravity too. But if you take off downhill, that's going to help you out. And runway surface has a huge impact. If it's a rough, let's go one extreme, a nice smooth gravel or a nice smooth asphalt, you're going to need less runway because you're going to speed up faster. Let's go to the other extreme of gravel or sand or snow on the runway, and that's going to, every time you hit a mud puddle, it's going to slow you down. It's going to harm your performance. Headwinds help you, tailwinds hurt you. With a headwind, it's free airspeed. You don't have to go anywhere to get air flowing over your wings. So you use less runway, you climb out steeper, and you have better climbing performance and takeoff performance. But you don't want a tailwind when you take off or land because it dramatically increases the distance that you need. Because you have to speed up to where there's no wind, and then you have to speed up from there to get the air flowing over the wings to start going flying. And when we're talking about all the same things apply on landing, and braking effectiveness should really only apply to landing, not takeoff. But how well your brakes work and how much you can apply the brakes before your tires break loose and start skidding. Okay, you don't want to skid because you have to replace tires if you do that, but B, you slow down slower if you lock up the brakes. Okay, most of these planes that you're flying don't have anti-lock brakes, so it's all up to you. You can't just mash on the brake pedals and then not expect it to not lock up on you. And I put a little snippet from the Cirrus Pilot's Operating Handbook down here, recommending you only that you have at least 2.5 times of the runway distance that the chart says before you take off. So if the chart says you need 1,000 feet to take off, Cirrus says you need actually 2,500 to do it safely, to give you a safe enough distance to take off. Most of your runways are going to be plenty long enough, but in case you go to some smaller strips, that's when you're going to run into that. Let me show you where that gradient is found. It's on the chart supplement and on the airport diagram. Let's zoom in on the chart supplement here. Here's the whole chart supplement for Brownfield. In case you didn't figure this one out, Brown is SDM because it used to be San Diego Municipal Airport, but then too many people confused it with San Diego Montgomery or San Diego International Lindbergh, so they changed the name of this one to Brownfield Municipal, but it kept the SDM designation. So up here in the runway information is where we're looking at now. Let's zoom in a little bit. And you see how long and how wide the runways are, and then we also see the what they're made of, how they're hard surface, that's the length, there's the width. This runway is made of asphalt and concrete. These are some weight limits for large airplanes that probably don't apply to you. There's high intensity runway lightings, and there's some PAPI lights on the left side of the runway. And runway 8 right is shorter and half as wide. It's only made of asphalt. and it actually slopes from one end to the other. So from 26, I'm sorry, from 26 left to 8 right, you're actually taking off uphill. So the airport surface is not totally even there. And if you forget how to use the chart supplement, we'll go to the answer key, the legend for the chart supplement, and they talk you through it. And for example, here, this is out of the test prep legend. They're telling us, since we're looking at runways here, you would find and what does ASPH mean? You look down here and it would tell you. You would just literally turn a few pages into the legend and it would tell you. But if you really want to know, there's all the acronyms for all the different runway surfaces. And then they only tell you what the runway gradient is or what the runway slope is if it's more than 0.3%. So if it's a really long runway, it could actually change elevation quite a bit from one end to the other. But if it doesn't ever do it steeper than that, they don't ever show you. And that's also, let's see how it's shown on the airport diagram. So this is still Brown Field Municipal Airport. And we were looking at 26 left actually has a 0.4% upslope from the east end of the airport to the west end of the airport. So if you're landing on 26 left, you're landing uphill. That's good for you because that decreases your landing distance. However, if you're taking off from 26 left, you're taking off uphill, which would harm your performance. You've only got 3,185 feet to work with. You don't want to have to be using any more than you have to because that is a fairly short runway. And they also show us on this chart, remember, they show us the actual elevation of the approach end of each runway. And you see there's actually about a 14-degree difference between taking off on 26 left and departing over the opposite departure end of 26 left. As opposed to the longer runway 28 right is almost 8,000 feet long. There is 18 feet difference between the approach end of runway 26 right and the departure end of runway 26 right. This happens to be the highest part of the runways in the whole airport. That's why they call it field elevation. If it was the hump in the middle, field elevation would be up here somewhere, and it would say field elev with whatever it is. But you see there's an 18-foot climb between this end of the runway to this end, but they don't say anything about slope here like they did on the shorter runway. That's because that increase in altitude and height is spread out over such a greater distance, more than twice the distance, that it's less than 0.3%, so they don't say anything. So the other point I'm making there is the lack of this doesn't mean that it's completely level. It's just not level enough for them to tell you about. So let's get into what's probably going to be everybody's favorite, the crosswind performance chart. This is one of the easiest charts there is, and this is for some reason one that everybody has a hard time with. Here's the Cessna version, and here is the FAA test supplement version of it. Now, what a crosswind performance chart is, it's again, same thing. You put in your two givens. Where the lines intersect, it points you towards the answer you're looking for. And since it's a chart, they give you an example. They're reminding you to go back to the 90s and get a plastic overlay for your overhead projector so you can put plastic on top of this and draw on the plastic without drawing on the chart itself. Or I'll show you a trick with the PDFs you can use too here in a minute. So in their example, there's a 30-degree difference between the wind and the runway. Step one is trying to figure that out. Okay, so a couple reminders. If I'm landing on runway 27, my heading is 270 degrees. I'm facing towards the west. So if the winds are coming from 360, that's a 90-degree change. I would start at 90 down here. If the winds are coming from 180, that's a 90-degree change. I would start at 90 degrees down here. If the winds are coming dead on to the runway, so I'm on runway 270 and the wind's blowing from 270, then I would have a direct headwind and I would come in on this line. If I had a 30 knot headwind, I'd be at 30 knots. And So my best advice there is to draw it out. Draw out the runway. You're like, okay, runway 33 is facing somewhere northwest about there, and if the wind's coming from, let's just pick a number 300, then there's how much difference is between my runway and the wind. It'd be about 30 degrees difference. If the wind's coming from 300 and I'm facing 330, then I'm going to have a left crosswind, and it's going to be what? What's it going to feel like? That's what this chart does. It breaks it into a headwind and a crosswind, so we can get an estimation of what it's going to feel like. It's going to feel like a direct crosswind, but it depends on the angle it's coming at. So here's how it works then. So on this example, there's 30 degrees difference between the wind direction and the runway. So there's my 30-degree line. And then I want to know, and the wind's at 40 knots. Okay, so if the wind is at 40 knots, then this whole arc right here is 40 knots. And what it's doing is it's saying if it was a direct crosswind, it would be 40 knots. If it was direct headwind, it would be 40 knots. And this chart shows us everything in between. Since there's only 30 degrees difference between the two and it's a 30-knot wind, I'm feeling a, I'm sorry, did I say 40? A 40-knot wind, I'm feeling a 35-knot headwind. And I'm feeling a 20-knot crosswind. So the wind is actually 40 knots in this example, but because it's not coming head on or directly from the side, I only feel about 35 knots of headwind and I only feel about 20 knots of crosswind. And the Cessna chart does it the exact same way. The only difference is the Cessna chart goes around the horn here to give you the options for taking off with a tailwind as well. So here's an example, almost the one I gave. If I'm landing on runway 27, I'm going to draw it out here. Okay, I'm facing west on a 270 heading, and the wind's coming from 330, coming from approximately there, somewhere in the northwest. If this was 360, this would be 315 if you want to do the quick math, and it's somewhere in between there. It doesn't have to be exact on this one, we're just approximating. So the degrees between 330 and my runway is going to be the difference between 330 and 270, and in this case it is 60 degrees. You can usually do the math. It's not headwind, that's not, I shouldn't have put it there. It's 60-degree difference between the two. You can do the math like 330 minus 270, but it doesn't always work. Let's say if the runway and the wind are splitting north, as in one's from northwest and one's from northeast, then you can't really do the math. You end up with a 500 something number, and it doesn't work out that way. So the wind, the difference between, in this example, where the runway's facing and where the wind's coming from is 60 degrees. So I need to find 60 degrees on here. Okay, and given to me was 20 knots. So the wind is from 330 at 20 knots. And here's our 20-knot ring. So wherever this line intersects this line is going to be my answer. Well, that's how I get my answer. So right there is where my 20-degree wind velocity intersects with my 60-degree difference in runway and direction and wind line here. And I go across to find, if I magic pen across here, that's how much headwind it's going to seem like to me. And if I magic pen down to here, looks like around 17.5 or so is the crosswind I'm going to feel. So make sure you get the headwinds and the crosswinds correct. That's the answer I'd be looking for there. And because this is everybody's least favorite chart, I'm going to do one more example. So let's say we're landing on runway 3, and the magnetic heading of runway 3 would be 030. Now this is why if you can't just do the math, it's not going to work for you, okay? You can't do 30 minus 330 because you'd end up with a negative number. And you can't do 330 minus 30, it won't give you the answer. So my recommendation always is to draw it out. Now, if I'm on runway 3, I'm facing 0, 3, 0 degrees. And if the wind's coming from 330, I have to figure out the angle between these two. What's this angle here? Now, I kind of picked these numbers because it's easy. Straight north would be 360. I'm 30 degrees to the right of it, and then the wind is 30 degrees to the left of it. If I add 30 plus 30, I end up with 60 degrees. All right, so both these are telling me that I'm 60-degree difference between the wind direction and the runway. In this example, it's only a 10-knot wind, so where does the 10-knot arc intersect the 60-degree line? So I'm going to feel when I'm taking off or landing on this runway with these wind conditions that I have a 5-knot headwind, but that I also have looks like about an 8 or a 9-knot crosswind. Here is an example of an FAA test question on the crosswind chart. And some of these you don't even have to do the chart. You can literally just figure out which one's most appropriate. Like this one, if they're saying the wind is out of the south at 20, which runway should I use if I only have a 13-knot maximum crosswind allowable component? So right now we're looking at the wind is coming from the south. The south is 180 degrees, right? So I'll tell you right now, if I have an option, I want to land on runway 18 because I'm directly into the wind. So if runway 18 is an option, that's the one I want. Otherwise, I want to land somewhere between, let's say, a 150 if I have it, to about a 210, because those are headwinds that aren't direct crosswinds. So let's see what answers they give us: 14, 24, or 10. All right, runway 14, I would have a quartering tailwind. Actually, that doesn't work. I would have a pretty good crosswind. If it were runway 24, I would have a really good crosswind. And if it were runway 10, then I would have also a almost direct crosswind. So in this example, 24 and 10 were both almost direct crosswinds. The only one that lands me into the wind would be runway 14, which would be this runway right here. So this would be the runway I would pick, runway 14, because it lands me with only a 40-degree crosswind component versus more on either one of them. And if that just confused you more than anything else, look around page 8, 10 or so in your book for more information on crosswind charts. Okay, now let's look at a takeoff performance chart. Okay, anything that affects how quickly we can speed up will decrease our takeoff performance. So again, high, hot, heavy, and humid equals danger, danger. And I will say one thing: at higher density altitudes, you have a higher ground indicated airspeed because the air molecules are less spread out, and that's how the airspeed indicator is working. That's how the pitot is working. So your gauge says you're going faster than you really are at high altitudes. So it's really important that you fly your gauge speeds, not out your window and what it looks like speeds to you. So if you rotate at what you think is 55 knots at a high density altitude because it looks like the ground's coming past you at 55 knots, you're not going to be at 55 knots yet. Your airspeed indicator will read lower because you need to go faster for the same indicated airspeed. Now all your POH numbers, your rotate at 55, your best glide at 68, your climb out at 78, like VY speeds and all those, they're all indicated airspeeds because you have an airspeed indicator in your airplane. So at a high density altitude, you will be going faster over the ground for your airspeed indicator to say the same thing. So make sure that you fly indicated airspeed speeds, especially at high altitudes, because the outside picture is going to look differently to you. And that's because you have a higher true airspeed at higher density altitudes. And true airspeed is indicated airspeed, correct for non-standard temperature. So just know that that's why it takes so much more runway to take off, because you have to accelerate to a faster speed at higher altitudes to get your airspeed indicator to read the right thing. And don't just trick it and try to fly off already, because your airspeed indicator is reading the same thing that your wings are. Okay, so your airspeed indicator is an indication of how much air is flowing over your wings, and if you remember back to our aerodynamics, your wings make lift dependent on the amount of air that's flowing over them. So, all right, so let's get into how to use these. Okay, here's a couple different Cessna 172S. That's the model of 172 takeoff distance charts. Now you see there are different gross weights. There's multiple takeoff distance and multiple landing distance charts for different weights for the Cessna 172. And you'll notice the number is a little bit smaller. So if you're a little bit lighter, you don't need as much runway to take off as if you were heavier. And everything else still goes from sea level to 8,000, sea level to 8,000. The temperatures still go from 0 to 40, 0 to 40. The difference being at an extra 150 pounds adds a considerable amount of distance. So let's go worst case scenario. We're high and we're hot. You see, under the same conditions, 8,000 feet, 40 degrees Fahrenheit, that extra 150 pounds that we're hauling around is going to take an extra 800 or so feet of runway, of distance to climb 50 feet. It's going to take almost an extra 350 feet of runway just to get airborne, and then an extra 800 feet total to climb 50 feet, just from the extra 150 pounds. So this chart, okay, you're going to have some quiz questions on this one. That's why I'm giving you an example here. So it's saying under this combination of altitude and temperature, in other words, the density altitude, but they don't give you just a density altitude. They're making it easy on you. So without looking at the example ones, let's say at sea level, I'm taking off at sea level, and it is exactly 20 degrees Celsius, then I will get those two numbers, because sea level is this line and 20 degrees Celsius is this column. And these are my two values then. It would take me 995 feet to get into the air, and it would take 1,690 feet from my beginning of my takeoff roll to climb 50 feet. So let's start out with a pretty easy one. Okay, so we're at our 2550 chart. We're at 20 degrees Celsius, and we're at 4,000 feet pressure altitude. I want to know how much ground roll is going to take off, and then our total to clear 50 foot. So again, we're in this column, and we're on this row. So those are my answers. Now, in this example, I don't have to add or subtract any of that distance, because I didn't talk about wind. I didn't give you wind because the winds are calm in this one, and we're not on grass or anything like that. So without any other variables, our ground roll is going to be 1440, and our 50 foot is going to be 2480. So there's your one example for this one. The landing chart's going to be the exact same, just the numbers down here on conversion might be a little different. We'll do one of those examples later. Let's go ahead and do one of these, like the Piper charts, like the figure you'll see on the FAA test. Here's the information they give you. We're at 90 degrees Fahrenheit, which is right there. We're at 2,000 feet pressure altitude, which is right there. We're at 2,500 pounds, which is this line right there. And we have a 20 knot headwind. Okay, so I'm just going to start from the back to the front. We need to intersect that line once we get there. Once we get there, we need to intersect that line. And let's start from the very beginning when put in our given information. There's our 90 degrees Fahrenheit, and that intersects our 2,000 foot line right here. So again, we're ignoring all the other arrows. That's for their example, and that's not what we're using. We're using this information now, right? So those two lines intersect right here. So that means we're done with that section. We move on to the next one. I follow these guidelines down. You see they kind of go down at an angle. I'd say right about there, because I can't draw a straight line with touchpad mouse. And now I've converted for altitude or for gross weight, and now I go off to the next chart. Now either follow the lines down to headwind or up to tailwind. Well, I have a 20 knot headwind, so I need to do my best to follow these lines down. We intersect there. And if my lines were all straight enough, my answer would come out right around there for ground roll distance. So this question asked for a ground roll, not for 50 foot. So I don't even have to follow the lines up or anything. Looks like halfway between 0 and 1,000, around 500 feet, and I was a little sloppy on some of my lines, so I think it's actually going to be more like 600 or 700 feet. But we'll see what the answer options are. 650. So if I got somewhere between 5, 6, or 700 feet, the only answer that is closest to all those would be 650, and that was actually the correct answer. So it works easier for you if you drag around like a straight line or a ruler, than instead of drawing crooked lines like this. And I'll show you how I do that on the PDF in a version. I just can't do that on the PowerPoint, this page here. I'll show you how to do that later on. Here's a link for you. I'll drop in the notes down below that can talk you through determining takeoff performance as well too. And it talks you through using these charts and how to use them and determine them if mine didn't work. All right, so that's how much run we need to take off and climb 50 feet. Well, now we need a climb chart to tell us how well we're going to climb. A quick reminder that Vy is your best rate of climb speed. You're going to get the most feet per minute at that speed. Vx is usually at a slower airspeed as you're climbing out. You're climbing out steeper, but you're not gaining altitude as quick. You're just climbing steeper, not faster vertical speed. Here's another link that'll be down below on a nice bold method article about the difference between Vx and Vy. And same thing as everything else. The heavier you get, the worse your performance. The higher density altitude, the worse your performance is going to be. And all the climb charts are based on you doing like that published best rate of climb, not a cruise climb. Generally, after we take off, we lower the nose a little bit and we increase our airspeed just a little bit, and we do a cruise climb. It's better for the engine, it's better for your visibility, but you're not going to get any guaranteed climb out of it that way. And then as you keep climbing, there's a point in time where the airplane can't climb any longer, period. It won't go up another inch higher. That's the absolute ceiling. And the service ceiling is when you can actually still climb just a little bit at 100 feet per minute. But as in you move around in the seat a little bit, it'll climb back up to that altitude, but that's about it. So again, Vy gets us the most altitude in number of minutes. Vx gets us the most altitude in the least amount of distance of your climb. But go see that other link for more info there. Here's a couple climb charts we have. This one's pretty straightforward. At this combination of altitude and temperature, let's say it's 0 degrees Celsius and you're at 6,000 feet, then if you climb at 73 knots indicated airspeed, you should get 515 feet per minute rate of climb. That's what foot FPM means. And again, always the notes. Above 3,000 feet, you need to be leaning even though you're at full throttle for your best engine RPM, because the air is less dense. You need to lean it to make as much power as you can. Next one over here is everybody's favorite. It's the time, fuel, and distance to climb chart. Now what this chart is showing us is how much, I'll give you an example of this one first before we move on to the next one. So I'm at 2550, I'm at 20 degrees Celsius, And as I'm climbing through 3,000 feet, I want to know what my climb speed should be and what my rate of climb should be. Now the speed's easy because at 2,000 feet and 4,000 feet it's 73, and I'm halfway between the two, so it's still going to be 73. But now I'm teaching you how to interpolate, how to get the number between two different values. And since I'm trying to go halfway between 2 and 4, I need to go halfway between those two numbers to get my answer. That's the easiest way to interpolate, and I'm trying to make it pretty easy on you in this class too, in this quiz. It gets a little more difficult in commercial ground school, you'll see. So there's a few different ways of doing this. If you're looking for the halfway point, because 3,000 is halfway between 2 and 4, it's easy. You can add the 2 and divide by 2, because you're really looking for the average between the two. There's a lot of different ways of doing it. I do these a lot mentally, and here's how I work it out. And if it doesn't work for you, then you didn't follow along, or it's just not how your brain works like my twisted brain does. There's 70 feet difference here between 625 and 555. So as in 625 minus 555, there's 70 feet difference between those two numbers. Half of that is 35. If I add that to the bottom value, there's my answer, 590. So exactly halfway between those two numbers is the number 590. Again, I know there's other ways of doing it, okay? If I did 625 plus 555 divided by 2, same answer, okay? I like to split the difference and then add or subtract. And this comes in handy, again, next semester in commercial ground school when it's not exactly halfway between the two. What if it was only a fourth of the way of the two? Then you can interpolate those values more accurately. But for now, I'm going to give you usually halfway values like that. This is everybody's favorite, okay? It's the time, fuel, and distance to climb chart. This shows us that when you're climbing from one altitude to another, what your climb speed should be, at that specific altitude what your rate of climb will be, but mainly when I'm asking you on this chart, I'm asking you these values: how many minutes it's going to take, how much fuel it's going to take, and how many miles it's going to take to climb from one altitude to another. So let's start with the basics on this one. If I go from sea level to 1,000 feet, it's going to take me 1 minute. I'm going to burn 0.4 gallons of gas, and it's going to take me 2 miles. If I go from sea level, let's go all the way to the end, to 12,000 feet, it's going to take me 28 minutes. It's going to take me 5 gallons of gas. It's going to take me 38 miles. So you can use this for your flight planning to determine how long it's going to take you to climb to get to your cruising altitude. So if you're just going from sea level, these are your numbers here. Okay, and it'll be very obvious, those of you who are listening to this part of the video and those who skipped through it, because what if you don't start from sea level? What if I start from 10,000 feet and I climbed to 12,000 feet? Well, that means I started from this number and went to that number. I need to find the difference between this number and that number. I need to find the difference between this number and that number. So if I climbed from sea level to 12,000 feet, remember it would take me 28 minutes, 5 gallons, and 38 miles. But if I start at 10,000 feet and I climb to 12,000 feet, it's only going to take me 8 minutes, 1.1 gallons, and 11 miles to do it. And on that one, see how much worse our performance is at high altitude? So just to climb 2,000 feet, it's going to take me 11 miles. Well, from sea level, it only took me 4 miles to climb 2,000 feet. And up at near the limit of your airplane's climb ceiling, it's going to take a lot longer. Okay, so let's do this question. Okay, so we're at 2550. Here's our example. We took off at 6,000 feet. We're climbing to 9,000 feet. So I need to go from these numbers to those numbers. From these numbers to those numbers. The difference between those that I'm pointing. Okay, these are from my other example. Okay, I'm telling you the temperature when you took off was 13 degrees Celsius. So that's going to come into play down here on our notes. So let's come back to that in just a second. So first we went from 6 to 9. So the difference between 10 and 17 is 7 minutes. I'm going to put it off to the side because that's not my right answer though. The difference between 2.2 and 3.4 is 1.2. And the difference between 13 and 22 is going to be 9. Okay. Now I need to see what else is handy on here. Okay. So the notes are so very important. Specifically that note right there, which tells me I have to add 1.4 gallons just for engine start, taxi, and takeoff allowance. So it takes me 1.4 gallons of gas just to get the aircraft in the air. And then these numbers start. So all the fuel used right here does not include the 1.4 gallons it took for you to get in the air in the first place. They can't just include it on here willy-nilly, because what if you were cruising at 10,000 feet and then you wanted to climb to 12,000 feet? If they included the 1.4 gallons on the chart, then you would not burn that because you've already taxied and took off. So that's why that's not included in the chart. You have to add it for the takeoff elevation fuel there. And then for each 10 degrees Celsius above standard temperature, you have to increase your time, fuel, and your distance by 10%. So that's why I give you this. So I'm telling you we're at 6,000 feet and the temperature is positive 13 degrees. If we go back quite a few slides, you remember what is the temperature supposed to be at 6,000 feet? If it's going to cool off 2 degrees for every 1,000 feet and we climb 6,000 feet, it's supposed to cool off 12 degrees. Well, if we start at 15, because that's the standard temperature, and we're supposed to cool off 12 degrees, it's supposed to be positive 3 degrees outside. So the international standard atmosphere at 6,000 feet is 3. I'm telling you, it is 13. So we are 10 degrees above standard temperature. Our ambient temperature is 10 degrees higher than it's supposed to be if it were standard. So we need to increase all our time, our fuel, and our distance by 10%. And this one's actually pretty easy. Okay, so it's times 1.1, because to add 10%, you can do 7 times 0.1 plus 7, or you just do 7 times 1.1. So this is times 110% is what I'm doing there. So really that's pretty easy. 7.7 minutes is what that is. Fuel is a little harder. Okay, what's 1.2 times 1.1? 1.32 gallons is how much fuel it takes then. But hold on, I need to add my note 1, my 1.4 gallons here, so don't forget to do that. Plus 1.4. It actually takes me 2.72 gallons. And that's to take off at 6,000 feet, use 1.4 gallons for taxi, start, and run up and take off. And then once I'm in the air, it's going to take me another 1.32 gallons to get there. So fuel would be 2.72, and the distance would be 9 times 1.1 is 9.9 miles. So there's your answers for this chart. If you're getting it wrong, it's because you're not watching this, and me telling you is not going to help anyway. But if you got it wrong, it's because you forgot what is the temperature supposed to be at altitude and what actually is the temperature at altitude. And then you have to apply note 3. The other thing everybody does wrong is they forget to add 1.4, because it adds up over time. Let's say if you do a flight where you've got 3 different stops. Well, that's 3 times you burned 1.4 just taxiing, starting, and taking off. And so that adds up after a while. And the other thing is, if you just say, okay, 3,000 feet, and just choose those numbers, well, it depends where you started. Okay, for example, if I took off at 2,000 and climbed to 3,000, it's only 1 minute, 0.4 gallons, and 2 miles. It's not 4:12 or 1.2 and 6. This is just a nice picture. I took this as I was climbing in a carbureted 172, Cessna 172 Skyhawk. And you see I'm like 1,200 feet per minute rate of climb. I'm at about 85 knot cruise climb here. And the cool thing is I'm climbing through 11,000 feet. I have super duper awesome climb performance. And this has nothing to do with the engine power of the airplane. This has everything to do with the mountain wave potential turbulence that I was using to get me to that altitude. So downwind of a mountain range, right, the wind kind of turns into a wave. It has updrafts and downdrafts. I'm flying parallel to a mountain range, and I'm in the updraft of the mountain wave right now, and the updraft has me climbing at 1,200 feet per minute. Now let's look back at this chart. How much should I be able to climb? Barely 260 feet per minute would I be able to climb at 11,000 feet. Here I am at 11,000 feet climbing at 1,200 feet per minute. It was just pretty. I had a good climb that day. That was a good time. All right, so that's takeoff and that's climb and climb checklist. Let's talk about cruise then. So it's up to you to set your throttle for cruise. How fast do you want to cruise? What RPM do you want to use? And because what do you want? Do you want to get there faster, but you're going to burn more fuel? Do you want to maybe pull the throttle back a little bit and burn less fuel? Save you a fuel stop, be a little more economical that way. I'll be honest, probably not. You're probably renting the airplane, so you're kind of in a big hurry to get where you're going. But if it saves you the 30 minutes of landing, taxiing, taking off, and climbing, it might be cheaper to fly longer at a lower power setting. So these charts give us those options. Your book talks about a few other things. The max level flight speed, that's as fast as you can go because your thrust equals drag. You don't have any more thrust to overcome any additional drag. Your maximum range speed is your lift drag max. That's like usually around your glide speed. And then your max endurance speed is wherever you have the minimum amount of drag. So max range means you're going to go as far as you possibly can. It's usually way slower than you want to go. Max endurance means the most amount of time in the air, or we would call that loitering speed in the observation world. Here's a cruise performance chart. I've already talked about range and endurance. Same thing before. Weight goes up, performance goes down. Density altitude goes up, performance goes down. Wind doesn't affect any of this stuff at all, but what wind does affect is how fast you go across the ground. If you have a higher ground speed, you get there faster. If you have a lower ground speed, it takes you longer to get there. But these numbers are you flying through the air, not you flying over the ground. So wind doesn't affect any of this information. Temperature obviously still does. That's why we have 3 columns there. So in the Cessna 172S model, they give you 2 pages worth of cruise charts. They're saying at 2,000 feet, at these different RPM settings, these are the different power settings, the different amounts of power your engine will make. This is max continuous power. And at this altitude, at this RPM, you will make this much power, you will go this fast, and burn this many gallons per hour. And then at a higher temperature, so all things being the same, if I'm still at 2,000 feet, if I'm still at, I set my RPM at 2,550, if it's 20 degrees above standard, I'm going to make less power than I did on a standard day because the air is less dense. I'm going to go slower, and I'm going to burn less fuel. That's because I'm so much more leaned out. The air is less dense, so I'm leaned out more because there's less air. That's what they mean by the recommended lean mixture here. So really what this chart is this is 6 different charts, really like 18 different charts in one. So let's just start with this one. So if I'm at 2,000 feet, only those values apply to you. You can ignore everything else. And there's 3 main columns here. So if the temperature is 20 degrees below standard, I would use this column. And if the temperature is standard, I use this one. And if we are 20 degrees higher than standard, I would use this one. And then, of course, you can interpolate between all of them if you need to as well. Now, think back to what our standard temperatures are. What's this temperature supposed to be at 2,000 feet? Well, if I cool off 2 degrees for every 2,000 feet, I'm supposed to cool off 4 degrees. And if I start at 15 minus 4, the temperature at 2,000 feet should be 11 degrees Celsius. So if I look at my OAT gauge and it is 11, I use this one. If I look at my OAT gauge and it's negative 9, I would use this one. If I look at my OAT gauge and it's positive 31, I would use this one. We can also figure this out before we get to that altitude. The winds and temperatures aloft forecast, it's in the name. They tell you what the temperature will be at those altitudes, so you can figure out the best one to pick for the cruise performance that you want. And somewhere else on the checklist, I have it cut off though. They're saying 75% is your maximum recommended power. So for instance, at low altitudes, on a standard day, 2550 RPM would give me a 77% power, but that's not good. I'm limited to 75%. So how would I get the number halfway between 73 and 77? Well, easy. I set the RPM halfway between those two numbers. I would set the RPM at 2525. I'll do my best to write it small. And I would get a number halfway between those two, halfway between these two, and halfway between those two. I would be flying at 116.5 knots true airspeed, and I'd be burning around 10.2 gallons per hour. If I was at 2,000 feet on a standard day with my RPM set at 2,525 RPM. Let's contrast that with the other end. What if I'm up at 12,000 feet? Okay, so I've got three columns, right? I've got below standard, standard, and above standard. The temperature at 12,000 feet is supposed to be pretty darn cold. So 2 degrees times 12,000 equals minus 24. So if I'm standard temperature is 15, minus 24 is what it should have cooled off that much up to 12,000 feet. Then it's supposed to be negative 9 degrees at 12,000 feet. So if it is, I would use standard column. If it's positive 11, I would use this one. And if it's negative 29, I would use that one. You notice at 12,000 feet, I'm at max redline RPM almost. I can't even get to max redline RPM. Redline's 2,700 feet. So the engine is not even capable of making 2,700 RPM at full throttle at 12,000 feet because the air is so less dense. So even at full throttle, I'm only making, on a standard day, 64% of my engine power. I'd be cruising at 119 knots, but I'm only burning 8.9 gallons per hour. So we see the difference here is 2,000 versus 12,000. I'm going faster. I'm 119 versus 118, and I'm burning less fuel to do it. 8.9 versus 10.5. That's because the air is less dense and the airplane has a higher true airspeed even though it's making less power. So higher is often better. Let's do one, maybe two examples. I pretty much already did 2,000 feet, but that's the example I'm giving you here. So I'm telling you the standard temperature is 11, and it's supposed to be 11 because it's supposed to cool down 4, and we've started at 15. We're supposed to be at 11 degrees. So to get our maximum horsepower, this is worth repeating, on a standard day, I need to go halfway between those two numbers, halfway between those two, and halfway between those two. So I would personally set it to 25 RPM, 2,525. That'd give me 75% of horsepower. I'd be cruising at let's see, there's 3, so 116.5 knots. And halfway between those two numbers, 10.2 gallons per hour. That's performance they say I should get at 2,000 feet on a standard day if I set my power to my max allowable recommended cruise power. All these cruise charts only give you max weight, so Obviously, you're going to get better numbers than that because you're going to be not max weight by the time you climb up to your altitude. Let's do one more. We're at 4,000 feet, so we're using this one. I'm telling you it's 27 degrees at 4,000 feet, though. What's the standard temperature supposed to be at 4,000 feet? Well, it's supposed to cool off 8 degrees. If we started at 15 minus 8, it's supposed to be 7 degrees, is the ISA. Well, it is 27. Now we know we're 20 degrees above standard. So we're going to use the 4,000 foot row, and we're going to use the greater than 20 degrees above standard column here. So remember, you get to choose what RPM to set and then the performance you get. Do you want to set 40% power RPM and take a month and a half to get to your destination when you pay by the hour? Probably not. I personally would set it here at your max allowable speed. So at 2,600 RPM, you set that with your throttle. I'm only going to be getting 72% power anyway, but I'm going to be cruising at 119 knots. And I'm only going to be burning 9.8 gallons per hour. So numbers are a little different than they were, even just up here at 2,000 feet lower. The number is a little bit different. We're going higher, faster, and we're burning less fuel up here at 4,000 feet than we did down at 2,000 feet. Now here's a Cirrus put together this chart in their handbook, and it's super handy. It's two charts in one, and it's got the handy temperature scale for you too. So I would save this personally right here. This chart I would save and have somewhere handy for you to refer to. And so what they did was in the Cirrus they said, let's say if you start at sea level and go to 5,000 feet. At 5,000 feet, the temperature is supposed to be 5. You'd climb at 97 knots. There's the climb rate you're supposed to get. It's going to take you 4 minutes, 1.7 gallons, plus the note for taxi and takeoff. And then you're only going to cover 7 miles. Then they say if you're going to go all the way to 17,000 feet, here's what the temperature should be. There's your climbing speed. There's your climb rate. And it's going to take you 21 and a half minutes to go from sea level to 17,000 feet. Now to put it in contrast, okay, what if I'm going only from 16,000 to 17,000? It's going to take me 2.5 minutes. It's going to take me 0.7 gallons of gas, and it's only going to take me 4.5 miles, right? So same thing, they just add on the easy temperature conversion for you here too. Pretty handy chart. Here's another way of doing cruise performance. The FAA is going to give you, this is an FAA figure. They would say, look at this chart, and they would say set this power at this altitude and what are you going to get, or some combination thereof. Really, with all these charts you put in the given information, and then wherever they intersect or wherever they point is the other thing that you don't have that you're supposed to be getting. Here's one example they might give us. So we're at 2450 RPM, which is what, let's see, this entire chart is cruise power, 65% max continuous power. That's our limit. And there's our different 3 temperatures. And if you notice, the RPMs are all the same. So don't let all these numbers freak you out. Basically, this is a fancy way of saying use this chart. We want to get 65% max continuous power at 6,500 feet with 36 degree higher than standard temperature. So we are higher than standard temperature by 36 degrees. So we're not going to use any one of those. And I'm at 6,500 feet. So I'm a little bit higher than 6,000 feet. So I want to know what manifold pressure will give me that. Will give me 65% power. And there's our temperature. So we're over here. Here's our temperatures. There's our altitudes. We're at 6,500 feet. Just a little over that number. I want to know what manifold pressure is going to get me. Let's see. Determine the approximate manifold pressure. Manifold pressure here. I'm a little bit higher than my top number. There's 6,000 feet. There's 8,000 feet. So I'm a fourth of the way between 21 and 20.8. because I have to interpolate between those two. So these are different manifold pressure settings, right here. This is the throttle setting on a complex airplane is what the manifold pressure is. The more throttle, the higher the manifold pressure. You don't even need to know that for this question because you have the given information. You're just trying to interpolate the answer. So my answer is I'm looking for 6,500, and if this value was 6,000, you can ignore everything else, and this value was at 8,000, I'm looking for something in between the two. All right, so if you do the math, there's only 0.2 difference between this number and that number. So the answer is either going to be 21 or 20.9. If you really wanted to do the math, it would be 20.95. But let's see what options they give us. 21. Because we're almost to 6,000 feet. These are the numbers that would give us the power that we want. The only variable was they only asked us what the manifold pressure needs to be. So of all the other numbers on this whole chart, honestly, the only two you cared about was that one, and the only closest answer was that one right there. 20.8 is wrong because that is at 8,000 feet, which is farther away from our target altitude than 6,000. So that's the closest answer. And once again, technically the answer would have been 20.95, which would round up to 21 anyway. All right, now landing, that's the opposite of taking off, right? It's all the same stuff. Okay, so a normal landing is not usually what's charted here. A normal landing is you kind of take your sweet time landing, you make it look nice and soft, you don't slow down, you don't burn the brakes, you don't flat spot the tires, you have a whole bunch of runway to stop. A short field landing has two main parts to it. It's landing at a spot, hitting your runway spot in a full stall, or being as slow as you can before you hit the runway and stop flying, and then decelerating. And we do that a few different ways. One with aerodynamic braking. So when you're pulling back on the yoke, you're trying to push the tail down, the nose up, the wings, the flaps, the belly, and everything else are causing aerodynamic drag, and that's slowing you down. That back pressure you're holding on the elevator is pushing the wheels down, which makes the brakes work better. So now you can use brakes too. So on a short field landing, it's all about hitting your spot and then slowing down. Things that affect your landing: the heavier you are, the more inertia you have, the longer it takes to slow down. Headwind helps you, tailwind hurts you. High DA hurts your performance. If you come in too fast, you float longer. You use more runway. If it's a runway surface, if it's slick or if it's bumpy, your brakes don't work as well. If you're sloping downhill, you need more runway to stop. If you're sloping uphill, you need less. And the conditions, that's if it's wet, slick, slippery, all those things. So really quick, I just want to talk about make sure you hit your landing spot, not before it, like this pilot does. This is awesome. This is not awesome. This. Don't be the sunbather. Oof. Okay, so that's not how you're supposed to do it. Okay, well, you asking what happened here? Well, this pilot got behind the power curve. They got slow, which made them get low, and they did the wrong thing, which was pull the nose up, which made them get even slower, which made them get even lower. The thing they needed to have done before going through this barbed wire fence was add power. Okay, so it's pitch for airspeed, power for altitude. There's a great video on why. And I'm sure this was a cool spot to plane spot, but nobody expected this pilot to come in and land. I mean, whew. Okay, don't be that guy. All right, let's figure out how to use a landing chart. Okay, it looks just like the takeoff chart, but it has a different word on it. It says landing instead. You would apply the same notes, you use the same pressure, altitude, and temperature, and you get the same answers. You interpolate the same way. So on this one, let's talk through this example. So we're at 2550. We're at 35 degrees Celsius. So we're going to have to interpolate between these two values. And we're at 7,000 feet. So at least we don't have to interpolate there. So then I'm asking you both ground roll and 50-foot obstacles. And lucky for you, I'm not giving any wind or runway information here, so you don't have to do any conversions on headwinds or tailwinds or anything on this question. So we're at 7,000 feet, so our answer is halfway between those two numbers and halfway between those two numbers. That's right, because I'm interpolating between 35 is halfway between 30 and 40. I need the number that's halfway between those two for my ground roll and the number halfway between those two for my 50 foot. You can divide by 2. You can find out the difference and add it and add half of that, whatever works for you. Okay. I'm mentally working this one out. If I subtract these two, there's 25 feet between that number and that number. So I add half of that to the lower number, which would be 12 and a half. So that's 797 and a half. Yes, I want you to be this exact. Now for the 50 foot, it's halfway between that number and that number. This one's a little easier. There's 40 feet between 1665 and 1705, so I add 20 to the lower one. If you're a glutton for punishment, then subtract 20 off the bigger number. You'll get the same thing. So if there's no wind on a level surface, dry runway, and I'm landing with my flaps down and I do everything like I'm supposed to, it should take me a total of 1,685 feet to climb over a 50-foot tree, or to descend over a 50-foot tree, land on the runway, and get stopped. From the point I land to the point I stop, it only takes 797 and a half feet, is what this is telling us here. Now, if there was a headwind, I would decrease distances by 10%. If there's a tailwind, I increase distances by 10%. The difference is 9 knots of headwind only decrease you by 10%, but you gain 10% for each 2 knots of tailwind. So if I have a 50, I'm sorry, that'd be a lot. If I have a 10 knot tailwind, that would increase my landing distances by 50%. So I would take this number times 1.5, and you would have the distance to land with a 10 knot tailwind. And they say up to 10 knots. This is kind of their tongue-in-cheek way of saying if it's greater than 10 knots, you shouldn't be doing it. Okay? They don't say it's a limitation, but you shouldn't be doing it because it's not charted. You're a test pilot if you do. All right, and then just to bring it home on the FAA / this is how Piper and Beach charts have it. The red lines, once again, are their examples. We're not using those. We're going to use, actually, well, I'm not going to do an example on this one. We will do an example on this chart, though. So go back to the other videos or earlier in this video and see how you use that. It's used the exact same way. On this one, we will do it. We want the total distance to land over a 50-foot obstacle, and we want to be at 3,750 feet, which is halfway between those two values. They made it easy on us, though, because it's standard temperature, but then we also have a 12-knot headwind. So we have to remember to decrease distances by 10% for each 4 knots of headwind. And that's decrease. Okay. So first, let's figure out what the number is. We're only looking for total distance, so I don't care about ground roll. All I care about is total distance. Now at 3750, I'm halfway between those two numbers, so I need the number halfway between those two numbers. Looks like there's 60 feet in between the two. If you do the math, 1195 minus 1135. So looks like the answer is going to be 1165, but not yet. I still have to compensate for the wind. So I have to decrease it 10% for each 4 knots. 12 divided by 4 is 3, so that's 30%, minus 30%. Now you could multiply and then subtract. The easiest way is to take 1165 times 0.7. That's mathematically the same thing as subtracting 30%, is by taking that times 0.7. And so let's do that. 1165 times 0.7. Our answer is actually 815. Really 816. 815 and a half. See how we did? 816. Look at that, huh? He did it again. All right, so to summarize this video, it was probably a little bit longer than I intended on, but because I gave you so many examples, and it is a YouTube video, so you can skip through it, the examples if you don't need them, and you can go back if you need to watch them again. But I can't let you. You can't skip videos that I didn't put in there and examples, right? So we went over different things that cause performance increases and decreases. You saw a lot of POH examples. Let's actually look at this Cessna POH and see kind of where it looks and where to find them, right? So let's come back to that. Here is our Cessna POH. Let's go all the way up to the beginning to prove you which Cessna we're looking at. The Cessna 172S model Cessna Skyhawk. This is the pilot's information manual. If it was in one airplane, it would be the pilot's operating handbook for that airplane. But since it's generic to all Cessnas, they call it a pilot information manual. They're all laid out in a standard format. Okay, Glenn PW. We're talking about normal procedures. That's your normal takeoff, climb speed, stuff like that. And then chapter 5, section 5 is performance. And so as we go through them, general just tells you about the aircraft, limitations. Let's see. A lot of conversions, just general stuff to know are in the general. Okay, that's where the name comes from. Limitations like your airspeed limitations, your weight limitations, your types of fuel you can use are all in there. Your RPM limitations. E is going to be emergency checklist, emergency procedures. These are, if you have any of those things wrong, these are the steps you take. They tell you your glide speeds under different settings, what to do under different emergency failures, and then for most common emergencies is what they put in there. Section 4 is normal procedures. This starts out with your pre-flight checklist. There's how you pre-flight, and there's what you're looking for when you do. And then they get down to how to start the engine, on how to start the engine, before takeoff or your run-up check. Here's your takeoff checklist. That should look pretty familiar to your Redbird checklist if you're in our simulator lab. Different procedures for short field takeoff. Now, to get the short field takeoff performance numbers, you got to follow these pretty closely. There's your cruise climb. There's your cruise power. That's why there's such a, now you know why there's such a big variation there. Then you set your power as desired somewhere between 2100 and 2700, because 2700 is the red line RPM. So you look at your cruise chart and see if what power setting you want, and so forth. Also, at the end of section 4, they start talking a lot about how to lean properly for ground operations, and when and how to lean during cruise flight. And really quick, I just want to point out, during cruise, the checklist over here, let me find you really quick. In here it says, during cruise, it says mixture lean for desired performance or economy. It doesn't say above a certain altitude or anything like that. It says if you're cruising, you should lean. And then later on in section 4, they go much more in depth on how to lean with using the exhaust gas temperature probe. And then they would get in here to also say there's your recommended lean, there's your best economy lean, and then they say lean the mixture for maximum RPM during full throttle climbs above 3000. And then, something many of your flight instructors are teaching you wrong, they tell you to lean the mixture for max RPM during all operations at any altitude, including those below 3,000 feet if you're using 75% or less power. In other words, if you're cruising and you can't cruise with more than 75% power, you should be leaned. Doesn't matter what altitude you're at. It doesn't matter what you're doing. Now, I will say, when you're in the traffic pattern, you're getting ready to go to full throttle again, and that's more than 75% power. So we just leave the mixture rich when you're in the traffic pattern doing touch and goes. But when you're cruising, it doesn't matter what altitude you're at. You should be leaned for when you cruise. Anyway, off my soapbox, and let's talk about performance. I can show you where to find these charts on your own. All right, this is a pretty big file, and you can get to it in Canvas. I recommend you have it, the digital version of it, and probably these charts yourself to use for the figures. and specifically get the PDF, and I'll show you a couple cool tricks here. They tell you how to use each one of the charts right here at the beginning, and then on the chart they give you examples on a lot of them too. I will ask you about, here's a nice temperature conversion between Fahrenheit and Celsius chart. I will ask you some questions about stall speed. I didn't put this in the video because it's not necessarily a performance thing, but it's a chart thing, and I want to make sure you can read charts. So let's say, and the stall speed's difference, and we're going to learn more about this in our next video for weight and balance, but your stall speed changes with the center of gravity is more forward or more towards the aft. And you see the difference here is not that great between them, to be honest with you. Looks like 1 knot difference at partial flaps is about the only difference in stall speeds near 172. It's a pretty stable, standard, easy to fly airplane. That's why it's such a good trainer. But with this one, the same thing. You just line up the information we give you with the information we're looking for. So if I say we're at rearward CG and where flaps are fully deployed and we're at 30 degrees of bank, there's your indicated airspeed, stall speed. Don't give me calibrated unless I ask for it. I'm asking you indicated because that's what your gauge says. As you increase your bank, the stall speed increases, and as you extend your flaps, your stall speed decreases. So you get to go slower with your flaps out, but the more you bank, the more heavier you feel, the higher your stalling speed. There's our crosswind component chart. What I like about the PDF and have your own is these guys right here. So they make it really easy and not have to try to draw straight lines. So let's say if there's a 50-degree difference between the runway I'm landing on and the wind, and I'm at 25 knots of wind, then I do this. It's a 16-knot headwind and a 19-knot crosswind. And done. And I don't have to worry about drawing straight lines, and that's going to be the best answer I can get. And I just put them on here, and I saved the PDF, and now I always have them for next time. We already went through the short field takeoffs, and literally that's why I have this, so I can highlight the one I want and make sure I give the right answer. And you notice there's a 20 max gross weight takeoff. There's a 2,400 pound takeoff chart. There's a really lightweight 2,200 pound takeoff chart. And you notice these numbers will be way different, way less than the other heavy numbers are. We went through rate of climb. We went through time, distance, fuel to climb. I've got my pre-arrow here so I can remind myself I'm going from one altitude to another one. And then I'll copy and paste it and put it on the other values to remember them. A few things definitely pleased with this chart. Remember, don't forget your 1.4 gallons for start, taxi, and takeoff. Here's the first page of cruise. Here's the second page of cruise. Just remember what the standard temperature is supposed to be. If you really want to go crazy, you can like write in the standard temperature there, so you don't have to calculate it every time. Range and endurance charts, landing chart just like the takeoff chart, and that's it for performance. And let's hop over to Canvas really quick and see anything else that we have coming up. And my student is falling behind here. We're in aircraft performance. Okay, there's the chapter you read. Here's the video you're watching and some other links, and you have a quiz on performance using these charts that we just went over. And then you've got another video to watch about weight and balance. I give you a lot of at least two different demonstrations on calculating weight and balance. Nice blank form if you want to work out it on your own, and then a weight and balance assignment you'll have to turn in. Where to find the Cessna performance charts and all the weight and balance forms and everything. Here's the POH that I was just looking at. That's this POH right here. And it's available in files for you. There's a blank weight and balance calculator if you want to, a blank weight and balance form. And that's probably it for the files in there right now. I think that's it for this video then. So get on Canvas, open up that quiz, start early in the week. Earmark a little bit more time for the quiz just because your first time through those charts and first time interpolating the values is going to take you a little bit longer, but you get way faster as you practice more. So just give it time. All right, thanks for watching, and I hope this helps. And if not, go back and watch it again. It'll help the second time, or look it up in your chapter, obviously, and then click the other supplemental links, the links below, if you need more help. All right, thanks.